Okay, so I was just reading through the notes I provided you guys on curves, and I have a lot to say there, and I think it would be helpful to you for me to just kind of give you a more simplistic version of that. And basically, the story is this: when we're given a curve, I mean, you can kind of picture it, right? So here's a curve. It's just some kind of one-dimensional thing. And how you describe that curve, it depends on whether or not the curve is in 2 dimensions or more dimensions, right? Now, if it's in 2 dimensions, if we're in 2 dimensions, then we have basically 3 choices. We might be able to describe the curve as a graph, right? In other words, y equals f of x, right? We might be able to describe it as a level curve. In fact, we can almost always describe something as a level curve. Level curve is something like some level function f of x comma y equal to some constant c. So a level curve is actually the solution set of that equation. I wouldn't usually say this to Calculus 3, but in terms of your other course, you could think of level curve as the inverse image of C under big F. And then the other viewpoint is as a path, or parametrized curve, or parameterization rather. And so there, you would be looking at, I often use R of t equal to, say, x of t, y of t. Now, each of these viewpoints has its merits. So the one thing is that the path of parameterization naturally has a sense of orientation. So this has is oriented. You can tell which way you're going. As time increases, you go in the forward direction of the curve. On the other hand, if we're looking at the solution set to an equation, you can't really orient it, right? In the same, well, a graph, I guess you could kind of think of left to right as being the positive direction. So, helpful to have at least one example. I'll try to keep it, keep it simple. So I'm talking about 2 dimensions to start with here, right? So let's see here. How about the example of a half circle? So we could look at this guy. So as a graph, and suppose it goes from r back here to minus r. R. Alright, so as a graph, we could write y equals to the square root of x squared minus r squared. Right, that's how to describe that curve. I'll make it red. No, make it blue. Make it blue. That's how to describe the curve as a graph. Right? To describe the curve as a level curve, we could perhaps write something like x squared plus y squared equals to r squared. Now, of course, the here I'm thinking of the level function actually just being x squared plus y squared. Right. Now that doesn't quite do it justice either, because in this context, if it's just that part, we actually need to, at this condition, y greater than or equal to 0, right? So that's one trouble with the level curve perspective idea is sometimes you have to cut down solution sets to focus just on the part you want. And then, of course, we have the perspective of a path. I would use, so you can write it, you can also write it as like x equals to x of t, y equals to y of t. So like I could write x equals to r cosine t, y equals to r sine t. If if you want to write them separately, but oftentimes we want to write them together as a single vector valued function of time, like this. In both cases, I need to specify 0 less than or equal to t less than or equal to pi. I need to say, or I could say t is an element of 0 to pi if you like. 0 to pi is what I would call the parameter space. And so that's the other perspective. Now this, again, has the distinct advantage of saying that actually the curve is going counterclockwise like that, you know. The orientation's missing from the other two's perspective. So those are three viewpoints. Now, so I would also say the following, that the curve C is parametrized by that. There are other parameterizations, like you could do r cosine of 2t, r sine of 2t, and let t go from 0 to pi over 4. Like you could speed up the curve by a factor of 2. There's all kinds of things you could do to parameterize the path. Okay, so that's 2 dimensions. These are the 3 viewpoints: graph, level, curve, path. Definition: r of t parameterizes level curve C equal to f inverse of, let's say, a constant k, I don't know, whatever. So what that would be is x comma y in R2 such that f of xy equals to k, using some of that inverse image notation from the other course. So r of t parameterizes a level curve if and only if f of r of t is equal to k for all t in the domain of R. In other words, you got a parameterization of a level curve if when you plug in the parametric formulas, it works. So this one, if you put x equals to r cosine t, y equals to r sine t, you plug them back up into here, it works because sine squared plus cosine squared is 1. All right, that's something we need to do. Moving over to n equals to 3 or higher. Well, n equals to 3, I'll focus on that for just a second here. The curve, I'll draw my coordinate axes like this, right? I'm no longer interested, or do I want to describe it as a level curve, because you can't fix one dimensions. You can't fix one-dimensional object in 3 dimensions unless you use 2 equations. So we already saw that with the symmetric equations for the line. So I really am not interested in the graph or the level curve perspective for n equals 3. Pretty much here I'm going to talk about I guess that's not entirely true. Sometimes I'll characterize the curve in terms of like being the intersection of 2 surfaces. But pragmatically speaking, to describe a curve in 3 dimensions, I really want to be able to say, here's a parameterization of it, I want 3 functions of time, or 3 functions of a parameter, and that is going to describe the curve. And it also would, you could think of it in terms of physics, it would be the position of a particle at time t that's traveling along the curve. You could do that. Okay, but admittedly, I mean, you could, in principle, think of describing a curve as like the intersection of 2 surfaces. Like, for example, one of the surfaces in R3 you could think about would be a cylinder. This is a right circular cylinder. You could give it an equation x squared plus y squared equals to 1. You could say, well, you're going to form a curve by the intersection of the right circular cylinder x squared plus y squared equals to 1 and like the plane. I don't know what plane is this. I'm not doing a very good job drawing it. I should have made these dotted. Too late. But the intersection it would be like this right here, right? That's the intersection of the cylinder and the plane. And like, you know, to give the formula for the plane, I would need something like, I don't know, I make up a plane. How about x plus y plus z equals to 1? Right? So if I wanted to parameterize that curve, what I would do is I would take care of that. I would say like x is equal to cosine t, y is equal to sine t. That solves this equation. And then I would fix the other one. I would say, okay, so I want z equal to 1 minus x minus y. 1 minus cosine t minus sine t. So there you go. There's a crash course on how to parameterize a curve which is formed by the intersection of two surfaces. You just kind of deal with one, take care of one, and then plug it into the other. And I'm not describing to you a foolproof algorithm to solve such problems. I'm telling you that these kinds of questions require some creative and geometric kind of leaps. But there you go. That's a parameterization for that curve. Okay, now we'll talk about in upcoming lectures other properties of the curve, like you can calculate its arc length, you can calculate, generally speaking, you can calculate its torsion in R3. We'll talk more about that. But generically speaking, a path in Rn is just, a mapping from t to r of t where you've got not 1, not 2, not 3, but n component functions, right? So now I have some. I think that those are the main points, right? And I have found a way to talk about things for, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll get through it here. 10, 11, 12. Here's curves in three-dimensional space. I actually have some nice pictures here. Like if you want to, you can take, if you have a parameterization of the surface that you're questioning, you can like feed in a parameterization of a circle in the plane and like glue it to the surface. I described that in this section. That's kind of neat. Here's some pictures of, this is called a helix. It's got that parameterization. This is the so-called twisted cubic. There you go. So, I mean, I do have some good examples, I think, but goodness gracious, just so many words, right? And those 2 pages I showed you, those are the main points. So that's it on curves in a nutshell. Next, I'll make a little video on surfaces, okay? Thanks.